name. Why that name? It's because if this was a quality, it's called Poisson's equation. And that goes back to the beginning of time. All right. But Poisson's inequality leads to exactly the same bounds as we had before. I mean, we will see this implies in a few lines that I looked at the average cost looks to be 0. So the proof that this implies this is the same. But we don't have a fundamental theorem of calculus for Markov chains or whatever. But we can cook one up. All right. So let's call it a theorem. I'll put that in quotes because we'll prove this. It's a theorem, a very simple one. But again, average cost is something that's often of interest in control, and we see that the average cost is bounded by some constant, which we've constructed this drift condition, so we know what this is. So we get a bound in the average cost as t goes to infinity, but we also get this bound in the transients. Right? And I want to say this over and over again, is that this average cost for large T is dismissed by people in operations research because they said, who cares about infinite T, I'll be dead. And there's this famous quote, in the long run we're all dead. And that's why they look at discounting. But people in operations research just don't understand the theory well enough. It turns out that when you optimize average cost, you really account for transients and the steady state. I'm going to make that really clear as I go along. So for example, when we optimize and get a good average cost policy, it gets really good transients as well. And the same can't be true for other criteria. All right, so again, that'll be developed. I'll explain that as we go through. That'll be clear to you by the end of March, or maybe the end of February. So this is again average cost. Yeah, I mean the thing that people in operations research typically dismiss is letting t go to infinity. They say, who cares about t equals infinity? And I'm going to convince you all that yes, you do care. Average cost, optimal policies say have really nice properties. Yeah. Okay, cool. So there it is. So I have to step back and do a bit more math. See, I can't prove this theorem without you guys understanding this notation. All right? So if I have some function h maps x to r, I define for you a this new function oh wait, you got the h. Okay. So on Thursday, I put this down, and I say there's always 3 of you who refuse to memorize this formula, and those 3 always, basically fail the course because you can't understand anything else I say without understanding this. So memorize it. Just put it in a damn flashcard, okay? And again, you've heard me screaming at people before. That's right. I think in another course. But really memorize it. Just put in a flashcard before you go to bed. Say, whenever Sean Mine writes pH of x, he means the conditional expectation. And it's also matrix vector multiplication because it's also an integral of h of x times the probability of going from x. I'll put a y there, sorry. And if you don't like that notation, it just means an expectation. You see, for each x, this is a probability measure on the state space, okay? And so when you want to take expectations, so fix x, if I want to take an expectation with respect to that measure, this is one way of writing that down. So these two, these are both just, abstractions, ways of writing this down. So if this thing has like a Gaussian density, you just integrate a Gaussian density, Or if this is discrete, it's a sum, all right? And doesn't this look like matrix vector multiplication, And again, as I said last time, if it's a discrete state space, this integral is a sum, and it's sum of, again, I'll say it again. So for a finite state space, it's really matrix vector multiplication, where you've envisioned functions as being column vectors. And the state y is like an index. That's the way to think about it. All right? Now, in the notes, I also defined some other things. And the thing, before we get into this stuff, I really need to make sure it's clear that this definition is consistent. And what I mean by that, you see, it looks like I'm just defining something totally different. I'm defining pH to be a conditional expectation, and p to the kh is another conditional expectation. I'm going k steps in the future. But really, this is the only thing you need. P to the k really is just a product of matrices, if you like, or a product, and more generally, when these are kernels. And what I mean by that is this. We define p times anything here, p times h. All right? And so when I say p to the kh, that's the same as p as defined here, hitting a function hk minus 1, which is that. And so you're really just multiplying these guys over and over again together. So again, the discrete time case, p to the k is the matrix product. Okay, and I'm going to prove this to you for k equals 2. I just before lecture I realized it'll just be useful to go through the math rather than rush into a proof of that where I know a lot of you won't understand it because you haven't absorbed the notation yet. Yeah, you see what I'm getting at here? I'm saying we could have defined the pk's inductively in this way. Once I define pk minus 1, I define pk for this formula. All right. All right, so let's do it. So this is the thing we're going to prove, but I guess not today, because it's already 2:40. Again, I need my fundamental theorem of calculus. For that, I need these guys here. Okay. So this is the claim. You know, and it's really confusing. Isn't that the definition? Well, it's not. I mean, here are the definitions. pH is a conditional expectation. P to the kh is a conditional expectation. And I just want to impress upon you that you can just, you know, get this conditional expectation by repeatedly hitting a function by p. You know, you take h, you hit it by p, you hit it by p again, you hit it by p again. Every time you hit it by p, you get a new function. P maps functions to functions. And I'm just explaining it for k equals 2. All right. All right, let's do it. So h1 of x equals the conditional, I'm just going to rewrite what it is. And you can tell this is going to be subtle because I've got to actually, oh, I forgot the h again. You can tell this will be subtle because I actually have to remind you that that conditional expectation is the same as that. You know, where I condition on the entire pass of the process. You know, remember the Markov property says that if I take a conditional expectation, give the entire past, I don't need all that information. I just need the present value. And by saying x equals x, it's just emphasizing the conditional expectations are a function of the variable of interest. You know, so, you know, is that too hard to read? H1 of, yeah. Yeah. Oh, I'm sorry. You're right. It's good that I'm rewriting this. Yeah. No, there you go. So that was my definition of H1. H1 is pH, and by pH, I'm taking h, hitting it by p to get a new function, and evaluated x. And that's always defined to be a conditional expectation. And then, and what's pH1? Well, I'm not going to write it that way. And fuck. I screwed up. Hey everybody, you can do this, right? You can add a +1 there, and a +1 there, and get your finger and rub, and make that into a 2. I need that, you'll see. Is that okay? Y'all made your changes? All right. pH1, that's equal to, yes. Yes, 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 yes. I think I should put a different symbol here. Okay. All right. All right. So you see what I'm getting at here, sort of?
Why didn't we go backwards?
Because I can do whatever I want. It's a time. Oh yeah, yeah. I mean, this doesn't. There's no t dependence anywhere here. All right. I can make t +1, and it's still true.
All that matters.
Yeah. Yeah. What I'm trying to get at is that the reason I did this is you can see it here. I've got h1 of xt +1. All right, and that's what this is really. I mean, I've said, you know, if xt +1 happens to be x, I plug in x. You know. But I can replace this guy by this guy, and just plug it in. All right? I have to get rid of that x and just say h1 of x t. And such. I really, really should have put in another color pen there. So h1 is that. All right. Okay, so this is where you have to review your conditional expectations. So the conditional expectation is, is a function of the variable that you're conditioning on, right? And if you don't give the variable, it's just a function of t plus 1. I can eliminate that and just put an xt plus 1 here. All right, and so now what am I going to do, everybody?
I think you're missing H.
I keep missing H. Why am I missing H? I never liked H. It's I should never use the letter H. So now, do you remember half of you remember anything from stochastic, from probability? I don't know. There's something, I hate this term. They call it the Tower property. I call it smoothing. So here I'm conditioning on a lot of information, everything up to time t plus 1. And here I'm conditioning on less information, everything up to time t. And it turns out they cancel. When I condition on a lot of information and then less, I can just ignore that. So I can ignore all that. And I already told you I can ignore all that, so just delete it. All right, and that's how I define p squared h of z. All right. Okay, so that again is called the Tower property. When you condition, again, a lot of information and then less information, it's the same as just forgetting that and just taking this and plugging it in. Okay? So that's the good thing is I'm not going to make you go through measure theory every lecture, but occasionally we do need this, so you do need to go and look at these basic things, The smoothing property is basic. It's the first thing you should have learned, well, at Illinois it was the first thing you would have learned. It's what you learn halfway through noise 1, when either myself or John Shea teaches the course. You'd learn the Tower smoothing property. All right, so basically the intuition in finite state spaces goes through. We basically can multiply these operators together, and in fact, I should write it this way as well. The probability in 2 steps of going from x to s is the integral of probability from going from x to dz. The probability in 1 step of going from z to s. Well, in fact. So that's another way of saying this, but again, that might be inscrutable to some of you, right? So this is a function of z, and px to dot is a probability measure. So I can integrate functions of z with respect to a probability measure. And so to compute this product, it really is an integral, which boils down to matrix vector multiplication in this discrete state space case. Right? Okay, so there it is. They're standing outside now. This is the setup, and like in 10 minutes, I can derive that theorem on performance bounds, now that you've accepted this fact. All right. All right.